Hello, welcome to the Water Research Foundation webcast on the project 5223, Guidance for Complying with the Lead and Copper Rule Revisions for Water Systems with No to Low Prevalence of Lead Service Lines. And my name is Jian Zhang. I'm a Research Program Manager with the Foundation, and I will be moderating today's webcast. To begin with, we have several housekeeping items to go through. Please submit your questions through the question box at any time. We will have a Q&A at the end of the presentations. Slides and the recording of this webcast will be available at our website here. You can actually download the slides now and access a link to the project page on the event resources on the bottom left of your screen. A certificate of completion will be automatically generated after the webcast. If you have any questions, please contact Michelle. Her email is here. Please also stay until the end to fill out a quick survey. We need to know how we do today. Let me introduce our presenters today. Richard Brown is a Vice President at the Cornwell Research Group. He oversees the treatment process evaluation and optimization, applied research, and the regulatory compliance for public water systems, including lead and copper, DBP rules, and residuals handling. He has been a PI or co-PI for many WRF projects. He's actually the PI for this project 5223. Our second presenter, Susan Keefe, is the manager of water quality for East Bay Mud in Oakland, California. She has over 30 years of experience in water treatment, water distribution, and water quality applied research. She is currently the chair of AWWA's Water Science and Research Division, and is a registered professional engineer and a licensed water treatment and water distribution operator in California. Susan has a bachelor's degree in civil and environmental engineering from the University of California at Berkeley, and a Master of Science degree from the University of North Carolina at Chapel Hill in water resources engineering. Our third presenter is Dr. David Cornwell, who is the CEO of Cornwell Engineering Group. He received his doctoral degree from the University of Florida, where he is currently an adjunct professor. He is working closely with many utilities, the WRF and AWWA, reducing lead levels in water. Dr. Cornwell has over 75 publications received. He has served on many AWWA committees and is a recipient of the AP Black Research Award, the WRF Research Award, and AWWA's Honorary Member Award. With that, over to you, Richard.
Okay, thank you, John. So this is WRF 5223, which includes two major parts of the project, two major objectives. One part deals with examining lead exposure from galvanized pipe requiring replacement, and the first two presentations will deal with that first topic, service line inventory guidance for systems, especially those with limited or no lead service lines, including some case studies and workshop findings. So in this webinar, I'm going to talk about some guidance for those systems with limited or no LSLs. Susan Keefe from East Bay Municipal Water Utility District is going to be giving the utility perspective, and then Dave Cornwell is going to be talking about using stable lead isotopes to identify galvanized pipe, GP, if that is a galvanized pipe requiring replacement. All systems must do a service line inventory as part of the LCRR in October 2024, whether they have lead service lines or not, or whether they're likely to have lead service lines or not. But sometimes those service lines, it may not be easy to find records for all of those locations. There are investigative methods that can be used, like sampling or artificial intelligence or some other specific techniques, but to be validated, they must either have be identified by records review or by two-point visual inspection, which we'll talk about some more here in a bit. So this graph is from the Cornwell et al. Project in the journal, American Waterworks Journal. Talks about the presence of lead service lines in the U.S. and talks about it by state. This graph shows smaller systems, less than 10,000 population. In red, then blue is the middle, and the black is the systems larger than 50,000. This graph is in arithmetic scale as opposed to log scale in the article. You can see this. What I wanted to point out in this figure is that there are some states with a lot of lead service lines and a lot of systems with lead service lines, but there also are quite a few that don't have many systems or much of the population with lead service lines. And in addition, you need to note that even in those states, like those ones in Region 5 that are in the middle of the graph that have lots of lead service lines, there still can be many systems in that state that don't have any and never have had lead service lines in their system. So the service line inventory requirements outlined in the LCRR are to complete it by October 2024. And when those are identified as either lead, galvanized pipe requiring replacement, which means it has a lead pipe between the galvanized pipe and the water main, or if you have an unknown pipe, you have to notify the customers of that within 30 days. The LCRR then stops, and the LCRI starts after that with updates and verifications that your approaches to doing the inventory and the replacements are correct. The service lines that are identified are lead lines that can be galvanized requiring replacement, unknown pipes where you can't determine it, especially by records review, and then the others are the non-leads, which are copper, plastic, etc. And that's the focus of this presentation is that. So when you use records view, you could to identify something as not lead, you need to either do records review or two-point visual inspection, and that, of course, is a very intense and involved process. So start off mostly with a records review to see whether you can classify it as not lead, or if your records review says it's lead, you can put it in those first two groups. And if you can't, in your records, you can't identify whether it's in those two groups, it goes in the unknown groups. The unknowns have to be treated like LSLs and GRR in terms of public education, but you do have to go to the next steps to evaluate what to do with those unknowns. So with the unknowns, you have to develop an elimination strategy. How are you going to evaluate those unknowns and determine whether they're lead lines, GRR, or not lead? And this needs to be done within 10 years. And also you need to do with it, before that's 10 years, or 7 years, you need to have some evaluation of how that strategy is working. This determination in your elimination strategy can be anything that's state approved. So it could be lead sampling, it could be artificial intelligence, it could be one of the in-pipe methods or other methods, emerging methods that can identify the lead material. And when you get to the end of that, your unknowns will either be in the lead group, either a GRR or an LSL, which means it goes in the replacement pool, and those pipes will be replaced within the next 10 years. Or if it goes in a not lead, it goes in the validation pool. Now at that point, it's still not classified as a not lead pipe because you have to go through additional steps after it gets in the validation pool, which we'll discuss next. So in the validation pool, it is not considered a not lead pipe until you do either records review, which you've already done in those previous steps, And in this step, the next thing you can do is do a 2-point visual inspection. Now that would be very, onerous if you had to do every single pipe, though that is one option. You can go to every single place that is identified as an unknown, or sorry, as a not lead, and do the 2-point inspection. But there is another option where you do a statistically significant portion of those sites and evaluate those sites. But if those are all not lead, then you can say that the whole group, all of the ones in your validation pool, are not lead. Another possible outcome is you do find one or more lead pipes, and then that's up to what you discuss with your state, because currently it's not currently defined. The statistical approach that we're talking about is a way to look at identify the pipes in your validation pool, verify the pipes in your validation pool without even looking at every single pipe. You come up with a statistically significant number of locations to investigate. And we'll talk about this a little bit more here in the next few slides. Some states are already allowing these statistical approaches, as mentioned here. This equation is a simplified equation that allows you to figure out the number of sites. This is the smaller or lowercase n that you have to investigate within the number of pipes in your validation pool. The validation pool number is that capital N or large N, and the factors in this equation are the margin of error, which is typically 0.05, the z-score, which is based on the confidence interval at 95% confidence interval, that z value is 1.96. And the other important factor is the variability of the population, which is that p factor. The p value is often used as 0.5 because that is the most conservative. And this example here shows for a system with 5,000 pipes in their validation pool, using the 95% confidence interval, a p equals 0.5 and the e equals 0.05, comes up that if you have 5,000 pipes in your validation pool, you can look at 357 pipes, and if those are all not lead, you can say that all 5,000 are validated as not lead. And this number here in this equation is identical to what's in the state numbers and in the LCRI. This p-value that's used, again, 0.5 is the most conservative because it assumes that you have non-uniform distribution of all of those sites in your validation pool. But if you have a better indication of what are the characteristics of the locations in your validation pool, it may be appropriate to use a higher P. Like if you knew that 85%, as shown in this slide, then you could use a value of P if you were sure that 85% of your locations had similar characteristics. Now, currently using another value of P would require state approval, or if it's modified in the final version of the LCRI to allow those other values of P. This table shows the number of locations in your validation pool in the left column. Next to that is the that value of n that we calculated with the p-value of 0.5. You can see at 5,000, it's 357. And these other columns show different values of p. So if you are at 0.85, like in the previous example, with 5,000 in your validation pool, you would look at 189 instead of 357. And if 189 were not lead, you could say that all 5,000 were not lead. But again, that requires state approval. So if you don't find any lead service lines, you can again say all of the validation pool is not lead. But if you do find some LSLs, first of all, you have to either replace that LSL or put it in your replacement pool so it can be replaced later within 10 years. Also, you can use the characteristics of those sites that have LSLs and try to investigate other sites within your system with similar characteristics to see if those are LSLs. Meanwhile, for the you can redo the pool with a second time to see if you can designate the rest of the validation pool as not lead. So we'll get to hear Susan Teefee talk about the utility perspective in the next slide, but some summary of this presentation. Again, doing the 2-point visual inspection is difficult. You can use the statistical methods to look at a smaller subset of those sites to make it a more manageable number. State approval is required if you do things differently, like using a different value of P, and for doing that, the evaluation of the unknowns, but that is possible, and you will need to work with your state to come up with the best approach for that. So again, Susan Teefee from East Bay Municipal Utility District will now talk about the utility perspective on some of these same issues.
Thanks, Richard. I am going to move to the next slide here. Can you see that okay? I'm going to jump right into the utility perspective. I am in Oakland, California, and East Bay Mud is a relatively old utility, around 100 years old. So we have some experience with old service lines, lead and non-lead. But I wanted to give a little bit of background. The data that Richard showed from the study that they produced in 2016, estimating lead service lines, if you plot that by state and then normalize it by per capita, you can see that there's significant regional differences across the country in the number of lead service lines. So it's a little hard to see on this graph. This is each individual state, and the top 5 on a per capita basis are Illinois, Ohio, Kansas, and Missouri. And the bottom 5 are all in the West: California, Arizona, Nevada, Hawaii, and Oregon. So in terms of the impact of this regulation, even though we don't have in the West very many lead service lines, we certainly have some work to do in terms of creating the inventory. Some additional background about East Bay Mud. We have about 1.4 million customers that we serve through roughly 385,000 service lines. We have a really clear delineation between the public side and the private side. Generally speaking, we'll have what we think of as the public side, a district service line that comes up and terminates at a water meter, and then from the water meter into the house is the private side. They're legally very separate for us, and it's common to install our side, the district side, and set the water meter a long time before the house may be completed. So we have no information about what happens on the private side of the water meter. We've also had a little bit of a jump on the requirement to create an inventory. In California, there was a state requirement that we create a materials inventory for all of our service lines. That had to be completed by 2018, but it did only include the public side. And then we had to have, kind of like in the LCRI, we had to have a plan to remove any remaining lead materials. But unlike the LCRI, that includes fittings. So we've been working on that for a little while. For us, we have pretty good records of our service line materials on the public side. They are paper records, and so it's pretty labor intensive to review them. But like Richard talked about, the AI methods or machine learning or statistical methods, we didn't do any of that. It's really just low-tech reviewing of records. We did develop a plan of how we're going to create our inventory and submit it to our regulatory agency, and they did approve that before we got started. And then a little bit of additional background, we've been practicing corrosion control since the 1930s continuously. And as a result of that, our tap sample leads are quite low and have been since the beginning of the LCR. So this graph shows where we are right now. We have no lead service lines, and we have no unknowns. Everything in blue here is copper or plastic. So almost 99% copper or plastic. And then the other slice here includes some funny one-offs, steel, asbestos cement, cast iron. We have, out of the 385,000, we have about 1,100 that are galvanized today. About 750 of those have copper pigtails, and about 380 have lead pigtails. And we know from our records that no lead pigtails were installed after 1928, except for a brief period during World War II. So the lead pigtails that we do have are quite old, more than 100 years in some cases. So looking back at our history, we do know that we installed lead service lines for a period of time. And it turns out that there's a pretty bright line between 1942 and 1945 when we did install them. There was a war production board that regulated everything apparently during that time, and copper and steel were pretty much unavailable due to the war efforts. But in our area, there were a lot of shipyards and Navy and Army facilities, and there was a lot of pressure to provide housing for the defense workers. So during that time, we did install roughly 7,500 lead service lines. And then pretty much as soon as copper was available again in 1945, we started using it. This graph here is month by month, the number of service lines installed, and then the colors indicate the material. So we use copper primarily. That's our material of choice for service lines. The gray is a little bit of galvanized services, and then pretty much we ran out of that. And from maybe the fall of 1942 until the fall of 1945, pretty much all lead. And then as soon as copper was available again, like I said, we started using that. And then also from our records, we know that as soon as as soon as copper became available again, we started pulling out those lead service lines. This graph here shows, this is a little longer time period. This is decades, so from 1930 up to the present. And we, this big jump from nothing up to roughly 7,000 was that period of time during the war. And then the slope is pretty steep and pretty uniform. This is removal of the lead service lines. So by the 1960s, we'd removed half of them. And then in the 1990s, when the lead and copper rule came into effect, we put some concerted effort into finding and removing the remaining ones. And so by about 2000, we had 97% of them removed. And like I said, because the records are a little bit tough to analyze, being paper, we missed some, but we think we've got them all at this point now. So that left us with the customer side materials. And as I said, we don't have any data for that. And we do know from looking at the plumbing codes throughout our history that lead was allowed up until 1986 when it was banned on the federal level. So in talking to staff, it became really clear they were quite adamant. I have never seen lead on the customer side of a meter. And we started collecting quotes, interviews basically with experienced staff. And these are just some quotes here from experienced plumbers that have worked on our system for a long time, also worked on the replacement crews that had just never seen lead on the customer side. And it even got to the point where there were people calling me at some point saying, you can add me to the list of people that have never seen lead on the customer side. They were all pretty adamant about that. So we decided to characterize everything on the customer side as non-lead. And we've definitely gone above and beyond the numbers that Richard was talking about. We have thousands of field verifications confirming that we don't have any lead on the customer side. So that just left these 7,500 locations where we know we used to have lead, and we needed to look for galvanized there because those would become GRRs in the new regulations. A lot of these are branched, and so in total we had to do about 10,500 field inspections. We're checking at the meter box and at the riser in the house, so it's a 2-point check. We used a contractor to do that work. We started in August of last year, and we should be finished by next month. So it's turning out that about 38% of those are galvanized today, and so those become GRRs, and we have mailed letters, and we're still in the process of mailing letters to all of those GRR customers. In addition, we are concerned about how the compliance is going to look like at those new sites because we didn't have any data from those locations. In the current lead and copper rule, the lead service lines and copper pipes with lead solder are in tier 1, so those are our compliance points historically. In the future, we're going to have to sample from galvanized pipes with lead fittings or GRRs. That'll be tier 3. And we're not going to be able to sample from the copper pipes with lead solder. And then there's first liter and fifth liter samples. So we started reaching out to customers that we now know have these service line materials. We've got a pool of 77 of them at this point, galvanized lines with lead pigtails. And this bottom row here, first liter and fifth liter P90 values, they're around 1 part per billion. And then the GRRs, we have about 71 of those, and first liter and fifth liter are non-detect. Even in this case, the average and the median is non-detect. There's just no lead in these GRR pipes for us. And in comparison, we went back and looked at all of the rest of our LCR data. So back in the 90s, when we still had some lead service lines in place, our first liter lead samples are shown in this first blue bar here. And the P90 of this data set is around 8 ppb. So less than the action level, but definitely not what we'd consider to be a low number today. The orange box are copper pipes with lead solder. We have around 500 of those over time, since the LCR began. And the P90 of that data set is about 4 parts per billion. The gray bar here, that's hard to see because the P90 of this data set is 1. These are just random customers. We have a program where any customer in the district can call us and ask for a free lead test. And we have about 1,700 of those right now. And the P90 of that data set is around 1 part per billion. So those are, and like I said, because we know our inventory relatively well right now, we're pretty comfortable to call those just categorically non-lead. So that's kind of our baseline. The next two, the yellow and the blue, are galvanized lines with lead pigtails, and the first liter and the fifth liter are comparable to our sort of random non-lead customers. And similarly with the GRRs, all quite low. So that's that. And then also we took those GRRs and we asked the question, does it change over time? So this graph here shows the time that's elapsed since the upstream lead service line was removed. And this is in years. So we don't have very many that have been removed recently. The bulk of ours were removed 30, 40, sometimes 70 years ago. And there's really not any trend. This line across here is our laboratory's detection limit or reporting limit, which is 0.4 ppb. So it's possible that if we had some newer ones, we could see a relationship here, but definitely in the ones that we have now, there doesn't seem to be any change with time. They're all quite low. So some additional work that we're doing on those galvanized pipes is we're extracting some of them and sending them to EPA in Cincinnati for analysis of the scale. We're sending 4 different types of pipes, public side, so district side galvanized pipes that still have lead pigtails today, some galvanized pipes that have copper pigtails, so those that were never exposed to lead. On the private side, GRRs that are very old. In the ones that we've sent most recently were removed more than 60 years ago. And then private side GRRs that are newer. And we're just finding the newest ones that we can. We're extracting in triplicate where possible, so 3 lines that have a similar age and similar water chemistry over their lifetime. And then we're having the customers take 10 sequential 1 liter samples before extraction. So we've got 11 pipes extracted so far. And And this is a graph of those 10 sequential samples. The green lines are actual lead service lines. We found 2 of them during this process. This graph goes from 0 to 16, so not super high numbers, but the highest green line, the fifth sample came in at about 8, and then it goes right back down again. In looking at the length of that service line, that coincides with where we would expect the lead service line to come in. And then the other green line that's dashed here, the highest one came in at the 10th liter, and that one had a service line that was about twice as long. So it's kind of what you would expect. The blue lines are 3 galvanized lines that have lead pigtails. So this is sort of newly extracted lead pigtails. And these numbers are all pretty low, but not 0. These are in the 1-ish range. And then it's hard to even see, but the yellow lines are galvanized lines that never had any lead on them, and they're all non-detect. And then below that are GRRs, customer side GRRs, where the lead service line was removed more than 60 years ago, and they are also all non-detect. So it's hard to find lead in these lines. Like I said, we're sending them to EPA in Cincinnati. They're splitting each of the pipes open and conducting X-ray fluorescence analysis from 3 different spots on each pipe. And then there's a kind of a semi-quantitative measurement, the sort of number of counts that'll help us determine what the individual elements are in each one. And then there's a quantification step after that. Between 18 and 30 spectrums from each pipe, depending on the length. And then there's some software that they use to analyze the counts and basically quantify basically the percentage of each of those various elements. And we don't have a lot of data back yet, but this is one preliminary graph that we've seen so far. Each of these is a different element. So the first set of graphs is iron, and the second set is zinc. From left to right, this is the copper pigtail, so basically a pipe that has never had lead on it, followed by a lead pigtail that's new. And then the yellow one is a newly extracted lead service line, and then the red is a lead service line that was removed a long time ago. So in terms of the iron and the zinc, these are all relatively similar numbers. But in terms of the copper, not unexpectedly, we see higher copper counts in the galvanized line that had a copper pigtail. And then in the lead ones, the recently removed lead service line had the highest lead count. And the GRR that had its, sorry for all the abbreviations, but the GRR that had its LSL removed decades ago was very low and comparable to or on par with galvanized lines that never had lead upstream. So that's as much as we have so far. We're still doing some additional analysis. We've got some more pipes to extract. But in general, what we're seeing is that if you have records and employees that have a lot of strong opinions about what they've seen in the field, you can do a fairly complete inventory based on internal records and interviews subjected to field verifications. It's a pretty expensive effort. We've expended 7 or 8 full-time equivalents and definitely more than $1 million on our contractor to develop the inventory. We're not anticipating any compliance problems with our new sites. It's a little concerning to me that both the GRRs and the galvanized lines with lead pigtails have lower lead levels than the copper pipes with lead solder, which, you know, in a sense, we're going to have to not monitor our highest lead concentrations moving forward unless there are some changes in the regs. We have around 4,000 customers that have GRRs. We're going to have to send them annual notifications that they have these GRRs. And we have to figure out a way to notify them when there's a disturbance. For us, that's going to be most difficult when a water main is repaired and dewatered. We haven't quite figured out how we're going to do that piece of it yet. but more taking a step back and sort of asking, what are we finding here? I'm not exactly sure what the presence of lead in the scale means in terms of lead release into the water. It's not clear if it's tightly bound or easily released, and what that means in terms of lead exposure for the customers. I'm not sure if it's appropriate to replace a GRR when we don't detect any lead in the water or in the scale. However, the LCRI requires replacement within 10 years, regardless of the time since the upstream LSL was removed. And also concerning to me, the annual notification of the GRR customers needs to include mandatory health effects language, including recommending that the customer have their children's blood lead level tested. We have to do that 4 times with 2 different methods, 2 letters, 2 phone calls. And we have been told very clearly by our lawyers, we cannot pay for private side replacement. So it's going to be a pretty confusing letter that we have to send repeatedly. And I'm not sure that our data support that kind of alarm, I think. And so what we're hoping to do here is develop maybe a more scientific basis for what would be an appropriate off-ramp, perhaps, for these GRRs where the LSLs have been removed a long time ago. And that is all I have. I'm going to hand it over to David.
Great. Thanks, Susan. Thanks for hanging in there so far, everybody. We're going to change topics then a little bit and move out of digging up ditches in the dirt and things and move to some more scientific discussions here, if you'll bear with me. It's important to keep in mind that it gets a little confusing that the way the proposed LCRI was written is that you do your first inventory, do this August, under the LCRR. So those are all the requirements that were in the LCRR. After that, is the way it's proposed, the LCRI would take over. And so all of the updates each year under the LCRI requirements will have you working towards getting rid of your unknowns and validating your non-leads, as Richard talks about. So it still leaves the question as we go forward as to one of the issues that comes up is, how do I know if a pipe is a GRR if I don't know if it ever had lead ahead of it? I don't know if it had a lead pipe. So is it a GRR or not? And this was raised by several people to us in the RFP. Susan raised it to us. I've got a lot of galvanized pipes. How do I know if it was ever a GRR? And so what we started looking at, and I'll give you some background because I think it has a lot of potential. It's worth thinking about because we have years of these identification for many utilities, unlike Susan, that are still going to go forward. So I want to talk a little bit about high precision isotopes. We haven't used those a whole lot in our profession. And we went through a series of proof of concepts, testing them on different ways, testing them on galvanized pipes. I'll show a couple. And then finally trying to answer that question, can we determine if a galvanized pipe is a GRR by using isotopes to determine where that lead came from? See if I can keep remembering how to do that. So again, without adding in construction records, how do we ever figure out if it was a GRR? So a novel method to determine that is isotope fingerprinting. And the technique has been used a lot in archaeology and forensics. And it's all based on the fact that ores, that when the world formed, ores all around the world have different kind of compounds of geology in them. And over time, those deposits that had uranium, thorium, actinium in them, they undergo decay to the stable leads. So these different areas of geology have different lead isotopic presence or desk maps, if you will. So those table ones are lead 206, 207, 208, and 204. The important things here, there are 4 isotopes that we can measure now that are all stable and that they come from different places in the country and the world, as a matter of fact. So we have a high precision lead isotope machine. It's called a mass collector ICP-MS with multiple detectors. You can do isotopes with an ICP-MS that you all are very familiar with, but unfortunately, there's some limitation with an ICP-MS. It doesn't give you as low a detection level. We can measure lead in the nanograms per liter. Not suggesting we do a PQL in the nanograms per liter, but with this machine, it can be done. ICP-MS does not detect 204, and 204 is very important to the analysis of this isotopes because it's a low-level isotope. It's different in the different geologies, and it's a stable. It's not a prodigy. So it's a stable isotope. So it's a critical, and without that, it's really hard to do separations. And the error bars with this method are in the third decimal point, so we don't even show them on the results. Whereas with an ICP, there's lots of overlapping associated with it. So you can see here, some of the first tests we did was gather a bunch of lead pipes from all across the country and found they all fall in a straight line. And we also did chrome and lead solder and brass fixtures, and they're all falling on this line. If they all fell in one glump, you can't separate them and see anything. So very nice. They all fell on different lines, and almost all the lead in the United States comes from Australia or what's called Mississippi Valley. It doesn't mean it's all Mississippi Valley, but that's a type of geology in the United States. And all of the lead now is mixtures of those in the United States. So this was a nice first step that, hey, the method's got some promise. We can identify these things. The next thing we did was start doing something very simple. This is waters from Flint. I can talk about Flint because it's kind of pretty public. This is some waters and pipes from Flint. So the little round circles are a isotope from a scale inside of a Flint pipe, and the water came out of the pipe. So it should be obvious, right? If I take a water sample and the system method works, and I take a scale out of the pipe, the two ought to match up. Well, you can see they matched up very well. They're just on top of each other. So the only one here was just a little bit differently, and perhaps that lead pipe had a different lead pipe upstream of it and threw those scales off just a little bit. So the very first thing we say, okay, hey, we can do this. Very simple basis. We can take water sitting in the pipe. There's no other source of lead but the pipe, and analyze it in the scales, and they match up. The next opportunity we had was to do some testing in copper with lead solder pipes. And the reason that came up because this utility was having some very high lead levels, and they don't have any lead pipes. And where is all this coming from? So this is a couple examples of things we did which furthered our knowledge in isotopes. If you look at this one over to the left, we're looking at an analysis of water and scale and solder in a copper with lead solder pipe. The solder sample was taken from outside the joint because, you know, you've seen these joints. They have lots of solder still on the outside. Many times when you open these pipes up and split them up and look at the joints, the solder is long dissolved unless it was a really sloppy job. So you don't see any solder inside of these pipes. But where was this lead coming from? So you can see these were right on top of each other. The solder isotope from outside of the pipe, the water coming from the pipe, and the scale, all for the same lead source. And so all of the lead in this scale came from the solder. And what happened, it turns out, from some other analyses, is the lead solder years ago dissolved off through galvanic corrosion, dissolved off. Some of it got caught in the scales, some went to the tap, some of it got caught in the scales, and then that lead, which was now lead 2, it's not solder anymore, it's now lead 2 in the scale, was trapped. The other thing we were able to do was look at solder in a pipe and a brass fitting. So this is the solder, again, from the outside. This is a scale. This is the isotope of lead in the brass fitting. And these are various scales. Well, they're between the two, right? Well, what's really interesting, if you would line up a distance line, these scales were right next to the lead solder joint. These scales were right next to the brass valve. So we're getting further into our verification that we can actually see mixtures of the isotopes. And, you know, in here, we've got an almost equal influence of the two types of lead source. And here, we're getting more and more towards the sources that are close to them. Just another along our way of what can we prove and what can we see with this. So testing galvanized pipes. This is whoops, I always do that with my arrow. And I always forget you can't see my pointer, so I hope I'll do a little better. But here's the classic fixture of what happens with a galvanized pipe and what we've been talking about here with the GRRs. Under the rule, if you have a lead pipe to the left, not a gooseneck, if you have a lead pipe to the left, and then you are followed that by a galvanized pipe, that's a GRR. The theory is the problem that is presented by EPA in doing this is that the lead came off of the lead pipe, either soluble or particulate form. It crossed across the galvanized pipe, and all of the iron in the galvanized pipe attracted that lead and got it caught in there. So that's why that one is regulated, whereas a galvanized pipe not preceded by a lead pipe is not. So the thought is the lead in the galvanized pipe has been accumulated higher because of the lead pipe. Now, as you see to the right there in that galvanized pipe, the galvanized pipe itself has lead. Almost all of our galvanized pipe came from what's called prime grade, Western grade galvanizing. It has, I said 1 to 2% because we kind of find that. The standard is supposed to be no more than 1.4%. So the galvanizing has lead, but the thought is more is going to come from the lead pipe upstream. Just a very simple, I'm only going to show a graph or two where we've got a lead pipe and a lead scale upstream of it. This is a GRR, so we've upstream of that. And here's the galvanized scale. See that they're all the same spot, as opposed to the galvanized pipe, which is over here. So here we can say that the predominant lead in this galvanized pipe came from the lead pipe. Very interesting. It's a GRR, right? That's fitting the concern of EPA. I'm not saying the concern is valid, just saying it fits the concern of EPA. Another quick example where it isn't quite so clear. Here we have a galvanized scale. Here we have the lead pipe and the lead scale. Here we have the galvanized pipe. We have an influence of both. So there's some partial lead from the lead pipe. There's some lead from the galvanized pipe. It's intermixed. And we also have a couple of these where it's not from the lead pipe at all, even though the lead pipe is there. But the vast majority of the ones we've tested fall into that category of the lead in the galvanized pipe came from the lead pipe. The lead in the galvanized pipe came from the lead pipe. So let's get to this question now of can we identify a GRR? What would we need to have to be able to do? Well, we don't want to take the GRR out and then figure it out. We've already taken it out. So we need to be able to do it in situ without harvesting the pipe. Somewhere we need to be able to access this galvanized pipe because we've got to correct a small sliver from outside of the pipe. So in the home, at the corporation stop, somewhere we've got to be able to get a small sliver from the outside of the pipe, not the inside. Then we collect a sequential water sample corresponding to the galvanized pipe location and look at those isotopes. I'm going to give two examples. The one on the left is we're looking at here the water sample and the galvanized pipe scraping from the outside. They are not the same, right? You and I can all see that they are not the same. There's a good chance this is a GRR because the isotopes in the sequential sample from this water do not match the pipe. Now, it could have picked up lead somewhere else in the house. It could have another source of lead as it moved, the water sample moved to the tap, but it could be a mistake classifying it as GRR, but that's what it appears to be. On the other hand, this is another utility pipe where we have the water sample and the galvanized pipe from the outside, its lead values, they are right on top of each other. This is not a GRR. Okay? Or if there's a lead pipe there, it had no influence on it. Might as well be not a GRR. Just quickly, I wanted to point out, as along with what Susan was saying, we tend to have, even these are all GRR examples of the percent lead in the scales. These are all GRRs. And you can see they run from 0.04% to 1.5%. Edwards did a recent research report, and he reported 0.3 to 0.8%, kind of in that same range as some of these. Compare that to lead. where it's often 68%, lead pipes at 60 to 80%. And also, as Susan's concerned, many of the copper lead solder pipes we analyze have more lead in them than the GRR galvanized pipe scales do. So again, kind of wonder, even though gallon pipes are falling apart, you kind of wonder about the lead problem. And here's just an example along the lines of Susan's. This is lead. This is flow-through studies in a rig at the city of Flint on galvanized pipes. And you can see lead levels here. This is 0 to 10 coming. This is directly out of the pipe, right? Not a tap sample. Collecting it right out of the pipe. Most of these have the air bars are, I mean, the prevalence bars, the box and whiskers are at 0. I mean, at 1, detection level. So almost all these are at detection level. So in summary, high precision isotopes are really proving to be valuable. In fact, we're moving now towards children's blood lead levels being checked with isotopes to determine the source in the blood. And certainly there's a lot of potential to be able to see if you have some GRRs as we move forward over the next period of time to have to more decide if something is truly a GRR or not. So with that, I know we've used up some of our time, Jan, but hopefully we have some time for a few questions.
All right, thank you all for all the great presentations. Yeah, we have received a lot of questions, and I don't think we have time to answer all of them. But don't worry, we will. If your question is not answered today, we will email you the answer afterwards. So let's ask some questions. Susan, I will start with 2 questions because there are many similar questions on these 2 issues. The first issue is about employee testimony and opinions. What about EPAs or states? Will they require a written testimony affidavit for that? How do they handle this?
That's a good question. We don't have any written guidance from our state. What we proposed to do in our plan was conduct the interviews by email, and then we save the email basically and document that. And then so we created a summary document that had the employee's name, their title, their job description, and then what they asserted. We asked them really just one question: have you ever seen a lead service line on the customer side? And then we just wrote down their answers. And then after that, we did a number of field verifications. So it was really not any more complicated than that.
All right, thank you. Another issue, the questions, I see that people from other states, Tennessee, Texas, Vermont, they asked about why you cannot pay, you are not able to pay for private site replacements. Can you use public funds or any other venues to pay for that? Yeah,
we asked our legal counsel for a formal opinion on that, because in the LCRI you have to have a plan for replacement, and if you aren't going to pay for the replacement, you have to say why, basically. And so we have a regulation in California that prohibits us from using ratepayer funds. And I'm not a lawyer, so I'm probably going to get this wrong, but in essence, we can't use ratepayer funds for things that are not directly related to the service that we provide. So a piece of pipe on private property is not considered part of our primary business of delivering water to us. And then there's other regulations about gifts of public funds, because it becomes the property owner's responsibility, or sorry, the property owner's property if we replace that line, and so we can't. Those were the 2 reasons that I was told. We could, in theory, I guess, go apply for a grant and then administer that grant. But I don't know how competitive we would be for such a grant when there are utilities that have actual lead service lines that could use them to be, could use that for replacement. So we haven't applied for anything like that yet.
All right, thank you, Susan. Dave, I think there's a question about the cost of this isotope testing. Is it a costly procedure?
Yeah, it's not too bad. Let me say that, well, I'm fortunate. I think you heard from the beginning, I'm not running a company. I have an appointment at the University of Florida, so I have access to all this great equipment. And other than going through us, the university itself is not allowed to do contract work. I can get it done, but there are 3 or 4 commercial laboratories that are able to do this. And I have not asked them cost, but that's something I can follow up in the question and answer we do afterwards. I can find that out for some people, some rough ideas, but it's not bad, really. It's more than just a lead analysis, but because there's a lot of prep time, you have to have clean rooms and things like that. But it's not outrageous. So let me say that I can't give more definitive now, but I will try to get that information for people.
All right. Has EPA accepted this isotope method to validate GRR? Yeah,
they probably haven't even seen it yet, but hopefully a few have today. But I would say that it's really left, the way it's written is it's really left to the utilities and the states to determine and accept what is a GRR and what is not, especially when you get into this thing of the lead line's not there anymore. So I think it's a very good scientific method. If anything, it errs on calling something a GRR. So I'm hopeful states would accept it and see the value, but it probably does need some more fleshing out and things like that.
Cool, great, thank you. Richard, here's a question for you. So the 2-point verification for visual inspection you mentioned, is that 1 on each side of the meter or 2 points on each side?
If this is a lead line that's all the way from the water main to the house, that would be 1 on each side. If there's been a partial replacement and there's lead on only one side, then it would be 2 on that lead side.
All right, thank you. I think there's another question for you. In your equation, there's a P, right? Modifying P requires a state approval. You mentioned that. Are those P values for statistical methods for the LCRR currently specified by all states, or do you mean just the states that currently allow statistical methods?
Yeah, that's a good question. And Richard had very limited time. And there is a journal paper coming out on this, as well as we have a report, of course, for the WRF, but with more details. Yeah, all that we have in a state or an LCRI is a table, right? They don't even say the equation they use. They don't see what p-value used. All they say is, here's the table. So what we have done is gone behind the scenes and say, okay, how would they have developed this table? And we went to the normal equations and statistical analysis used for surveying and say, yes, this has to be the equation they used, and they had to use these values because it matches their table exactly. So we then altered the P, because statistically it would make sense to alter the P. Many statisticians do that. They often don't use a 0.5. And so we have presented the opportunity for utilities to try to consider convincing their state that they can use a different P, because like in Susan's case, we don't have any lead lines. Well, why should P be random, non-uniform sample? So we've also been working with AWWA Government Affairs Office to see if EPA is willing to consider an inclusion of some language in the LCRI. So when I say right now P would have to be varied, it's because there's no mention of even what P is in any of the states or even the LCRI. So it's a whole new field again of trying to explain to everybody where these numbers came from and why statistically there's justification for not using the equation exactly as was done in those tables.
All right, thanks, Dave. Let's take the last final question for today. Dave, regarding the inventory map, are we okay to use the term possible lead instead of lead?
Well, That's not the way the LCRI is written. The state may accept it. The state's eventually supposed to give it some database to EPA. So whether we'll come back to you or not, I know why you might want to do it, but that's certainly not the way the LCRI is written.
All right. Thank you all. Our time is up. Thank you so much for all the great presentations, and also thank audience for all the great questions. We will answer them, email those to you. Otherwise, have a good day.
Thanks, everybody.